Hi everyone, this is Ramalinga Prasad Kuppa. Welcome to my channel Pharma World. Today's topic is molecular rotational resonance for residual solvents estimation. The standard test method for residual solvents or organic volatile impurities is USP Chapter 467. As a supplement to the existing test method, the new molecular rotational resonance (MRR) technique is developed. This method is suitable for many residual solvents that may be difficult to estimate using the traditional headspace GC with flame ionization detector. This technique enables direct analysis of residual solvents and provides detailed spectral data for both identification and quantification. Let us learn more on this in this video. Present status. Residual solvents are estimated as organic volatile impurities as per USP General Chapter 467. This chapter 467 is a validated and established test method existing now for many of class 1 and class 2 solvents. This method uses headspace gas chromatography technique. Headspace gas chromatography technique analyzes volatile compounds by capturing the vapor phase of the test sample solution. There are two basic procedures, procedure A and procedure B. These two procedures A and B are used for water-soluble articles and water-insoluble articles. European Pharmacopoeia Chapter 2.4.24 also deals with estimation of residual solvents in pharmaceuticals. In European Pharmacopoeia, there are two systems prescribed, System A and System B. System A is generally used. System B is employed normally for confirmation of identity. The specific procedures are used for class 1 and class 2 solvents. Class 1 solvents are highly toxic category and class 2 solvents are relatively less toxic. Class 3 solvent is generally estimated as loss on drying, that is LOD test. Class 3 solvents are least toxic and generally be estimated as loss on drying test at specific temperature depending upon the type of the residual solvent present in the product. Let us see the new approach. Molecular rotational resonance (MRR) technique utilizes the microwave region of electromagnetic radiation. Microwave range of electromagnetic waves is with wavelengths ranging from 1 millimeter to 1 meter or frequencies between 300 MHz and 300 GHz. Microwaves are a form of non-ionizing electromagnetic radiation. The attractive feature of MRR for residual solvent analysis as a technique is that it can bridge the analytical gaps of conventional methods for analysis of low volatility solvents. This energy of the microwave region corresponds to the rotational energy levels of molecules in gas phase in complex mixtures. The range of radiation has only rotational energy levels which are used to identify as each solvent with three-dimensional spatial arrangement that has specific narrowband absorbance. Based on the quantum chemistry, the rotational transitions, each component is identified very precisely and quantified accurately. The quantification will be like a fingerprint identification of the solvent. The spectra obtained is compared with the theoretical simulated spectra for confirmation. This is like identification of specific person by thumb impression for a fingerprint identification system. If fingerprint matches, that means the solvent is identified unambiguously. MRR spectroscopy is a complementary method to the headspace GC for low volatility solvents like dimethyl sulfoxide DMSO, water soluble acids and certain volatile amines. The flame ionization detector FID in headspace gas chromatography sometimes find it difficult for such low volatile solvents to estimate accurately. This MRR technique can be used effectively for getting accurate estimation. This technique allows a direct analysis of residual solvent mixtures and provides detailed, unambiguous, clear spectral data for both identification and accurate quantification. The sample solution can be directly injected into the system for analysis. It can be used as an online real-time monitoring of the residual solvents. Its online compatibility allows for a real-time monitoring, supporting pharmaceutical manufacturing processes like process analytical technology PAT and quality by design QBD concepts. The headspace GC method cannot quantify accurately the low vapor pressure solvents including 2-methoxyethanol, 2-ethoxyethanol, NN dimethyl acetamide, NN dimethyl formamide, ethylene glycol, formamide, N-methylpyrrolidone and sulfolane. The FID in headspace GC needs adequate vapor pressure for volatilization of the solvent. So these kind of solvents are difficult to get estimated accurately. The MRR technique with continuous headspace sampling can directly analyze the residual solvents with more efficiency and the data will be information rich, well defined, reproducible, highly characteristic and extremely sharp. This can estimate the spatial arranged cis trans isomers also very clearly. This unique selectivity gives MRR a key advantage in which mixtures of all types of isomers can be analyzed directly without the need for chromatographic separation. Also, MRR has the potential to reduce the time of analysis of mixtures containing diverse volatile chemicals, including residual solvents listed in USP 467 chapter. Let us see how the analytical method works. The sample is injected into the system inlet and heated. This is the procedure. The sample solution is introduced into the sample inlet and heated. The vaporized molecules will be pushed into the vacuum chamber with an inert gas like neon with purity of more than 99.999% where they go into supersonic expansion. Neon is used as a carrier gas. It should be pure to ensure that the carrier gas does not generate extra impurities in the sample injected. The molecules are excited by a broadband microwave radiation where each molecule absorbs energy. At this stage, each component solvent absorbs energy at specific frequencies from the microwaves. This data is acquired through Fourier transformation system. Fourier transformation is a mathematical tool transforming a signal from the time domain to the frequency domain. The data is compared with the predicted theoretical spectra and quantified accurately. This is the final stage where the frequencies data generated is overlapped with the theoretical spectral data and confirm the identity of the residual solvent. With the help of necessary spiked standards, the quantification could also be done accurately. Let us look into the other advantages. The MRR technique is useful for solvents like acetic acid, formic acid and dimethyl sulfoxide. These solvents cannot be estimated accurately by the existing headspace GC test methods. Other solvents including ethylene oxide, formaldehyde, acetaldehyde, carboxylic acids, volatile amines and sulfur containing species can be directly analyzed by MRR technique without any derivatization. Here, derivatization into a volatile compound is not necessary. Also, necessary correction factor for derivatized entity may not be necessary. This is a new thinking and approach suggested by the USP NF stimuli article on analysis of residual solvents, that is dated on March 26, 2025 and is open for comments up to May 31, 2025. Try to understand and see if we can contribute for the development of this technique. Thanks for watching. For more videos, please do subscribe, like and share. Also, please leave a message in comments box for any further support. Thank you.